Hi students. So today we will discuss the second lecture of the pipelining under the computer architecture. As we have already discussed that what is the pipelining, what is the impact of the pipelining, and what are the hardware changes are required in the pipeline structure with respect to the unpipelined structure. As we have already discussed that by incorporating the pipelining, it increases the throughput of the CPU. So which means the number of instructions completed per unit time will be increases. But at the same time, we can also say that the execution time of individual instruction will not be reduced in the pipelining. In fact, if we will look at the overall performance, then we will find that the execution time of the each instruction will slightly be increased, and this increase will be due to the overheads of the control of the pipelining. So the increase in the throughput means that a program runs faster and has the lower total execution time even though no single instructions run faster. So it means the single instruction will not run fast, it will take slightly more time, but overall if we look at the number of instructions executed in per unit time, that will be increased. Actually the throughput will increase. So if we look at that, the fact that the execution time of the each instruction does not decreases put the limit on the practical depth of the pipeline. The pipelining is going to increase the throughput. So what will be the depth of pipelining? Depth means how many maximum stages can be included in a pipelining. The practical depth of the pipelining is also have some sort of restrictions. So all these things we have already discussed in the last class. So today we will try to discuss what are the difficulties. So as we have already discussed in the last class, all the advantages are there, all the benefits are there. So today we will discuss, is there any problem, is there any concern, or is there any issue, or is there any hurdle in the pipelining which can restrict the overall performance of the pipelining. So today we will discuss this. So today we will discuss the major hurdles in the pipelining. So these major hurdles are also called as the hazards in the pipelining. So today we will discuss the different hazards. So what are the hazards or what are the major hurdles within the pipelining? So these are the situations which prevent the normal execution of the next instruction. So whatsoever the next instruction we want to execute, these hurdles or these hazards are prevent the normal execution. It is the situation which prevent the normal execution of the next instruction in the stream from its designated clock cycle are called the hazards. So whatsoever the designated clock cycle is allotted to perform or to start a instruction, if any hurdle which prevent or will create some sort of problem for the pipelining and will delay the starting of that particular instruction or the completion of that particular instruction, that will be called as the hazards. So hazards are reduce the performance from the ideal speed up. Whatsoever the ideal speed up we want to achieve under the ideal circumstances with the pipelining structure, it will reduce that particular performance. So basically three types of hazards are there, which are also called the hurdles or problems, whatsoever we can call it, which limits the effectiveness of the pipelining. And these three hazards are structural hazard, data hazard, and control hazard. So although we will discuss the each and every hazard in detail in the coming lectures. So what is the structural hazard? The structural hazard will arise due to the conflict of data path resources. Let's suppose during the execution of a program, and say processor is having a data path or a resource, say two instructions are trying to access the same hardware resource in the same cycle, that is called the structural hazard. For example, if we will compare it to the example, let's suppose we are having a one memory source with us, and let's suppose two different instructions want to access the same memory within the same cycle for two different instructions, and whatsoever the hurdle will occur due to this situation will be called as structural hazard. The second is called data hazard. Data hazard arises when an instruction depends upon the results of the previous instruction in the way that is exposed by the overlapping of the instruction in the pipelining. So data hazard will arises when, let's suppose, instruction number 2 want to manipulate some sort of operands, and still operand is not available within the processor, and it is the expected operand which instruction 2 want to manipulate will come as a outcome of the first instruction. So then processor will have to wait for the execution of the first instruction, and then only it will be able to get the data for the second instruction. So this is called the data hazard, when an instruction depends upon the result of the previous instruction and which instruction is yet to be executed, and data is yet to be available and data is not available, and that point of time whatsoever the delay, whatsoever the stall, whatsoever the bubble will be introduced by the system to wait for the result, that is called the data hazard. Third is the control hazard. The control hazard will arise from the pipelining in case of branch related instructions and the other instructions in which the sequence of the instruction will have to be changed. As we know that what is the normal sequence of execution of a processor? The normal sequence of execution of a processor is it will execute the instruction in sequence. Whatsoever the instruction number 1 will be there in the program will be executed first by the processor, and then second, third, fourth, and process will go on. But in case of branch related instructions in which the need of the program is to change the sequence, will have to jump to some another location which is not in the sequence, then program counter will have to change the address, and so it can jump to the specified or required location of the branch instruction. In these cases, whatsoever the delay will be introduced, and that particular delay will be the delay in which program counter will prepare the actual required address where or from where the next instruction will be executed from the assigned branch location. So whatsoever the time will be taken by the processor in the pipelining due to this particular situation or due to the branch related instructions, that is called the control hazard. So again, I already told to you, whenever hazard will happen, whenever any hazard will exist, or whenever any hazard will occur or such type of situation will occur, so it is necessary to introduce the delay between the stages of the pipelining. So the sequence, whatsoever the sequence till now we have discussed, in which first of all fetching, then decoding, then execution, memory access and write back will happen, but due to these hazards the delay will be introduced in between these stages, and that delay, unwanted delay due to these three reasons, will be called as stall, or sometimes it is also called as bubble. So now we will try to understand what is the pipeline hazard and what will be the impact of that pipeline hazards on the performance of the program with the help of different diagrams. As we know that the hazards depends on the properties of the program. As we have discussed that the three types of hazards are there: structural hazard, data hazard and control hazard. So what is the need of the instruction within the program? Accordingly, either the structural hazard will exist, either data hazard will exist, or control hazard will exist. That will depend upon what type of instructions are written in the program. That is why I have written this: the hazards depends upon the properties of the program. So what will happen whenever there will be hazard for any nth instruction, say? So let's suppose these are the different instructions which processor will have to execute, and these instructions are I plus 1, I plus 2, I plus 3 and I plus 4. And these are the clock cycles or cycle number 1, 2, 3, 4, 5 and so on. For the first instruction in the first clock cycle, opcode will be fetched. For the second cycle, first instruction will move to the decoding stage, and at the same time the second instruction will be fetched. And at the third clock cycle, the first instruction will move from decoding to execution, and second instruction will move from fetching to decoding, and third instruction will be fetched and process will go on. Now, under what circumstances any hazard can occur? This particular sequence looks like a normal sequence. So from this particular diagram, there is no problem. But where the problem will exist? Now we'll come to this. Let's suppose we want to execute a program, and let's suppose the first instruction of that program is the load instruction, in which the data of the memory will have to be loaded to the any register, and then say rest of the instructions will have to manipulate that data, say for example. Now we will assume that, as we have already discussed, that the hazards are depends on the properties of the program. So we will have to assume one scenario, and we will assume this is a scenario. Let's suppose the first instruction of the program is the load instruction. So what will happen in the case of load instruction? Initially, the opcode of the load instruction will be fetched from the memory. Then it will be decoded by the decoding register. After the completion of this decoding register, the processor will come to know that now processor will have to load the data from the memory, and whatsoever the address is required from where the data will have to be loaded from the external memory, all those things will be completed within this execution unit. And after the completion of this execution unit, whatsoever the data we want to read from the memory, and address of those memories, and so address of those source and destination will be ready, and then within the fourth clock cycle the data will be fetched, data will be read from the external data memory, and then in the fifth cycle whatsoever the data we have already received and that will be there in LDM, low data memory, will move to the required destination. Whatsoever the register where we want to write it will be written back to the memory. So if we will look at this, during the fourth cycle, what processor is going to do? Processor is going to access the data from the external memory. It means processor will have to access the data from the external memory, and during the accessing of the data from the external memory, processor will send the address on the address line, data lines, data will come on the data line and control line. So address, data and control lines along with the external memory will remain busy during this point of time. Now we will look at the instruction I plus 3. The third instruction, fourth, which is I plus 3, and it is third from the load instruction, and during the fourth clock cycle the first instruction was busy to read the data from the memory, second was busy to execute the instruction I plus 1, and third was busy to decode the instruction I plus 2. And in the fourth cycle, the first stage of the I plus 3 instruction will have to be fetched from the memory. So now we will try to look at this. In the fourth cycle, one instruction number 1, which is the load instruction, is already accessing the data from the memory, and the another instruction number I plus 3 also want to access the data from the instruction memory. And again we will have to go one assumption. Let's suppose only single memory unit is there for that particular CPU or for that particular machine. So now problem will occur, as only one or a single memory unit is there, and from one memory unit with one set of address, data and control lines, the data from that memory unit can be accessed by only one stage or for one instruction only. But here if we will look at this, due to the pipelining structure, need of the program or need of the data path is to read the data for two parallel instructions within the same cycle. So this particular problem in which only one single memory unit is there, one resource is there. So now this single resource and two different instructions want to access this single resource within the same cycle. So this particular problem will call the hazard. And whenever this situation will occur, and as we have already discussed that under this situation, delay will have to be introduced, and the name of that particular delay is called stall. So a stall or bubble will be introduced or will be entered at the fourth clock cycle. Okay, so now what will happen to the rest of the instructions? All the instructions introduced after the nth instruction. So here nth instruction means affected instruction. So here instruction I plus 3 is the affected instruction. So but actually at the fourth machine cycle, the I plus 3 instruction will have to be fetched from the memory, but due to this problem, due to the structural hazard, processor cannot assess it and will introduce a stall or a delay. So whatsoever the instruction after this will always require the stalls, will always be delayed by the number of stalls. So let's suppose if one stall will be introduced over here, then in actual, due to this problem, the I plus 3 instruction will be fetched in cycle number 5. So naturally, as I plus 4 was expected to fetched in clock cycle number 5, but at clock cycle number 5 the I plus 3 is fetching. So that is why again I plus 4 will also be delayed by one clock cycle and process will go on. So which means each and every instruction which will comes or which will be introduced after the instruction, after the affected instruction, are also required the stalls. Okay, but on the other hand, there will be no impact on the instructions which have already been initiated, and all those instructions which are initiated before the affected instruction, say nth instruction, and in this case it is I plus 3. So all the instructions which have already been fetched or which have already been executing, and these are called unaffected by stall. So the execution time of these instructions will not be changed, it will remain same, but execution time of the rest of the instruction including I plus 3 will be changed as one stall will be introduced. So each and every instruction will be delayed by one cycle. So this is what is the pipelining hazard. So that is why we are saying that it is not easy. It looks like easy. The pipelining structure is looking very easy, and there are so many advantages we can say that, but for the implementation point of view, by pipeline structure which is having more number of stages, the implementation will become complex. So complexity to implement the high depth pipeline structure will become difficult. Okay, so this was the simple pipeline. What is the impact of pipeline? So although we will discuss the structure, data and control hazards in detail in the coming lecture. Okay, so now before we'll move to the next to discuss the structural hazard or data hazard or control hazard, we will try to understand how can we evaluate the performance of pipeline with stall. If stall will there, then what will be the impact, and if stall will not be there, then what will be the performance, and how can we measure the performance of a pipelined structure. So as we know that the speed up is a unit which used to measure the performance of any structure. So here by using similar speed up we will use to measure the pipeline structure. So initially we will consider the ideal case. Everything will go smoothly. There will be no hazard within the pipelining for a program, and if there will be no hazard, so naturally there will be no stall. So if there will be no stall, so what will be the speed up? Speed up will be the number of pipeline stages, that is the pipeline depth. As we know that the equation or method is used to calculate the performance or speed up of a pipeline structure, then that will be equal to, and it is equal to average instruction time of unpipelined upon average instruction time of pipelined. So that will be equal to number of pipeline stages or pipeline depth. So this was the when under the ideal condition. Time for pipeline structure, it will be the average instruction execution time of unpipelined structure upon average instruction execution time of pipeline structure. So it will be equal to the pipeline depth. Okay, so if again we will go and bifurcate it with respect to the number of cycle per instruction and the clock cycle time, then it will be rewritten as CPI unpiped line, means CPI is where clock cycles per instruction of unpiped line into clock cycle time of unpiped line structure. Okay, so it is the average instruction execution time. Similarly, the average instruction execution time for pipeline structure will be the CPI of pipeline into CC time of the pipeline. So now we will bifurcate it into two terms, CPI unpiped line and upon CPI pipeline into CC time unpiped line upon CC time pipeline. As we have already concluded in the previous lecture as well, the pipeline reduces the average execution time per instruction. This reduction in the average execution time per instruction will be due to the decrease in CPI or due to the decrease in the clock cycle time. So now we will try to understand what are the equations are required to evaluate the speed up with respect to the decreased with respect to the CPI or with respect to the CC or clock cycle time. So first of all, we will consider that the pipeline decreases CPI. First of all, we will consider this. The pipeline structure decreases the CPI, and for this particular case, we will have to make one assumption, and that assumption is we will have to assume that the clock cycle time for unpiped line is equal to the clock cycle time of pipelined structure. So we will ignore the CC time overhead due to the pipelining. So here in this case we are going to ignore it. So once we will ignore it and we will assume that the CC unpiped line and piped line is same, so this factor will be nullified, and only this factor will be used to evaluate the speed up of the pipeline. So the resultant speed up of the pipeline will be equal to CPI unpiped line upon CPI pipeline. Okay, so now if we will consider that the CPI pipeline ideal is equal to 1, as we can see that after the completion of this fifth cycle, if there will be no stall or there will be no hazard, one instruction will be executed in each cycle. One instruction will be executed in each cycle from the pipeline structure. Although the one instruction is not going to be executed in the one cycle, but effectively with respect to the throughput, one instruction will be executed in one cycle. So we can see even after the completion of 5 cycle, instruction 1 will be completed. After 6, I plus 1 will be completed. After 7, I plus 2 will be completed. Then I plus 3 will be completed, and process will go on. If there will be no order, so initially we will assume that, let's suppose the pipeline structure is ideal structure. There is no stall in this. So what will be the CPI? The number of cycle required per instruction will become 1, as we can see that. The effective number of clock cycles required for one instruction is 1. After the completion of every cycle, we are able to, or our structure is able to execute one instruction. Okay, so what will happen if there will be stall or there will be any hazard? So now we will try to calculate it again. The CPI pipeline will stall. So CPI pipeline will stall, which will be what? Let's suppose now we will go and look at the instruction number I plus 3. in which one stall was introduced, and that particular stall was introduced what? 1 clock cycle. This, due to the introduction of this stall within the sequence, the I plus 3 instruction will be delayed by 1 cycle. If there will be no other stall or other hazard, then it will be completed after the 9th cycle. Actually, the expected completion time was of this instruction was at 8th cycle, but in actually due to this stall, it will completed after the 9th. So that is why there will be a delay or CPI, whatsoever the CPI for this particular instruction will be increased by 1. So that is why we have written the CPI pipelined with stall. This was ideal. Here we have considered that it is unity, it is equal to 1. But CPI with pipeline and under stall circumstances, it will be CPI ideal, whatsoever the ideal time was required, that is 1 plus clock cycle of the pipeline stall per instruction. So how many clock cycle extra will be introduced per instruction, that will also be added within this. So the net CPI for pipeline with stall will become CPI pipeline ideal plus CC of pipeline stall per instruction. So now we'll put these values and then speed up for using pipeline will become using pipeline under what? With stall will become CPI unpiped line upon 1 we will consider the CPI ideal, CPI pipeline ideal plus CC of pipeline stall per instruction. So this will be the equation which can be used to calculate the speed up. So in the simplest case, in which we will consider that each instruction takes exactly the same number of CC, which is equal to the number of pipeline stages or pipeline depth, and then the speed up using pipeline for the pipeline with the stall will become pipeline depth upon 1 plus CC of pipeline stall per instruction. It will be equal to pipeline depth if there will be no stall. But if there will be stall, then this value will be changed or this will be reduced. Okay. So, or how can we calculate the performance of CPI under ideal condition with no stall and with stall as well. Okay. With respect to CPI. Now we will consider the second case, in which we will consider that the pipeline decreases the CC time. So for this assumption, we will assume that the CPI of unpiped line will be equal to CPI of pipelined time, and that will be equal to unity. Okay. So the CPI, here we have to consider the CPI pipeline ideal. So we will consider it is equal to unity. So the speed up using the pipeline in terms of CC. So okay, the speed up using the pipeline, this we have already discussed that this equation, and CPI pipeline with stall, if we will assume that CPI pipeline with the stall, that will be CPI ideal plus CC of pipeline stall per instruction. After replacing the value into this equation, CPI or speed up pipeline will be equal to CPI pipeline unpiped line upon CPI pipeline. This equation will be replaced with this one, so it will become this equation. Now we will have to put the value of CPI pipeline ideal will be equal to 1, so it will be CPI. So the speed up using pipeline in terms of CC will be equal to 1 upon 1 plus CC of pipeline stall per instruction into CC time unpiped line upon CC time pipeline. Okay. So this is the under circumstances whenever there will be any stall. But what will happen when the pipeline is perfectly balanced? Means each and every stage is perfectly balanced and there is no overhead and there is no stall or there is no hazard. So under those circumstances, the CC time of pipeline will be equal to CC time unpiped line upon number of pipeline stages. So number of pipeline stages will be equal to CC time unpiped line upon CC time pipeline. So what will be the speed up? Speed up will be pipeline depth. It will be pipeline depth. So we will replace this, which will become pipeline depth upon 1 plus CC of pipeline stall per instruction. So that will be equal to pipeline depth if there will be no stall. So this is the way how can we evaluate the performance of a pipeline structure without the stall, which will be the ideal condition, and for balanced pipeline with no overhead. And we have also discussed that how can we evaluate the performance or speed up of the pipeline structure with the stalls. If stalls will introduce, then what will happen? Okay, so this is all about what is the hazard, what is the impact of the hazard on the performance of the pipeline structure, and how the performance of the pipeline structure can be evaluated with and without the impact of the hazard. Thank you.